So yesterday we discussed about the line spectra, Bohr's atomic theory, and which is failed to explain more than the one atom, so that which is only capable to give the line spectra of the here. What do you say? Only one atom, so that so for one atom, it can gives the complete picture about that. But here, which is failed to explain about the more than one atoms. That means if you want to get the line spectra of the here helium, lithium, like that, which is failed to explain. And also here, whereas in H alpha, you are going to be getting here two closely packed lines, which is of 0.013 angstroms. So that is also failure. Why these two close lines which are going to be getting here? So that's why here, when Sommerfeld, which he was entered into the picture here, he is going to be introduced that here. What do you say, N5 and so here just want to show you, yeah. So here azimuthal and radial, N5 is the azimuthal, and also here NR is the radial quantum members. So based on this, he has been calculated that the atom which could not be revolve around the nucleus in a circular orbit, the atom which is going to be revolve around the nucleus in a elliptical orbit. That is the one greatest revolution which was introduced by the Sommerfeld. And also here the velocity could not be remains a constant here. When it is going to be moving and changing the path here, the velocity is also going to be changes here. Okay, so the energy levels of the hydrogen atom, so you can see here how the when the transition is going to be takes place, so that from higher energy level to the lower energy level, when the emission is going to be takes place here, higher to the lower here. So that in which series, that means Lyman, Balmer, Paschen, Bracket, Fund, different types of series are there. So based on that, in which series which is in visible region, and which series which is going to be in ultraviolet, okay, and also IR region, so that you can easily calculate. Yeah. Next one is the vector atomic model. So here, according to the Bohr's theory, you need to know about that here, the energy which is going to be quantized in magnitude. That means which one is going to be quantized here, that is for the size. Okay, so but here quantum theory which is going to be consisting that here, insisting that the quantization of orientation of the orbits. Okay, so how the electron or the atom which is going electron which is going to be revolves around the nucleus here, that is based on this spatial quantization. So in which direction it is going to be here, the electron is going to be moving here. And also what is the purpose of the what is the direction of the applied field, as well as the magnetic field which is going to be applied to the atom here. So here the direction which is also going to be quantized, so that here which can explain about the how the spectrum which is going to be gives the spectral line spectra here, so that how by applying the magnetic field as well as the electric field to the atom here, how the lines, spectral lines which are going to be splitting. Okay, that means the applications, that means for magnetic field Zeeman effect, as well as if you apply the electric field, the splitting of the spectral lines, which is related to the Stark effect. Okay, most important short questions. So that is comes under the spatial quantization. Next, the spinning of electron. So which can give the fine structure of the Uhlenbeck and Goudsmit, which have been introduced the concept of spinning of electron here. So the spin electron S is plus or minus 1/2. So here the electron spins about its own axis, which is addition to the orbital motion here. So that the spin which you may be introduced, the quantum number is S. Next, another one is that principal quantum number, which is going to be denoting here small n. So which can gives the number of cells according to the Bohr's atomic theory. The value should be 1, 2, 3, and so on. And later is orbital quantum number, which is going to be call it as a small l, so which is denoted by small l here. So that which is similar to the azimuthal quantum number, that is n5, and here if n equals to 3, for example, if n equals to 3, you need to explain with respect to, in examination point of view, we have to give one example. Okay, while you are going to be writing this may be asked as a question, not as a short question. Please remember this. So for example, if n equals to 3, principal quantum number n equals to 3, L values, that is for 0, 1, and 2. So which is going to be here, if L equals to 0, which maybe represents the selection, that means here 1 represents the p electron, and if L equals to 2, which represents the d electron, that means L equals to 0 means yes, okay, s orbital, that means L equals to 1 means p, and L equals to 2 means d. Here there is no print mistake is there. So next, the orbital angular momentum PL of the electron, the formula is PL suffix L. Okay, so that may be written as here LH by 2 pi, but according to the wave mechanics, so the L value should be square root of L into L plus 1 into H by 2 pi, or else you need to write it down that H by 2 pi may be a H cross. Okay, no need to worry here. Next, spin quantum number, that is also in place of L, you have to write it down square root of S into S plus 1. Okay, orbital is L into L plus 1. Next, total angular momentum J equals to L plus S. Is it clear? So J values must be here the sum of the here orbital as well as the spin quantum numbers. So here J values must be plus or minus L plus or minus S. That means plus F, plus of, as well as the minus of here. So here plus indicates that a vector parallel to the L vector, and minus indicate anti-parallel. Okay, so that what are the L values? If it is going to be considering L equals to 1 means p orbital, which consists of here S values must be off, J values must be 3 by 2 or 1 by 2. Why? Because of 1 plus 1 by 2 is 3 by 2, 1 minus 1 by 2 is 1 by 2. This portion. Okay, so here therefore the total angular momentum Pj equals to square root of J into J plus 1 H cross, or else you need to write down H by 2 pi, whatever it means. So here to explain the splitting of the spectral lines, let us consider that more number of quantum numbers. So that another one is the ML. That means ML means magnetic orbital quantum number. So you can easily, you have to draw this diagram here based on that L values, ML values, magnetic orbital quantum number. Okay, so how these values are going to be varying here, minus L to plus L, including 0. So bottom portion is minus L and the top most is the plus L. You can see here. Okay, so like that series. This one. This is the plus of plus L, minus L, 0. Okay. So ML values must be -2 plus -1 and 0 plus 1 and plus 2 when if L equals to two values, so which is known as spatial quantization. Next, magnetic spin quantum number, ms values. Spin quantum number, one is here for plus of, another one is the minus of, so that the projection of the spin vector along the direction of the magnetic field. So which is also, one is the parallel, another one is the anti-parallel. So the total means here also mj values, ms plus here ml values, that is you can easily see that how the j values, angular momentum values with respect to the magnetic field here, how it is going to be changed. So this is about the vector. Next, this may be asked as a Frank Hedge experiment. You need to know about that here. What it is, let us discuss about the briefly. So according to the Bohr's theory, the atoms, so that will be in the ground state when the electron which is going to be revolve in first orbit, so that the atom which is going to be radiates the energy, when the atom is going to be radiating the energy, so that the electron from a ground state which is going to be should be raised from a higher energy state, so that which is called as excitation. That means when the electron which is going to be absorbs such an energy here, the electron may not be in a stable ground state here. It is trying to jump from the ground state into the higher energy. Higher energy means here excited state. Okay. So in this case, the electron which may goes into the higher energy state. So that if the excitation is high, so that the electron which is going to be knocked out the atom, and this process you can call it as a ionization. So the potential that are necessary for these two conditions, which are known as critical conditions. So that here excitation potential, which is also known as radiation potential, or else you have to say that resonance potentials. So these may be expressed in terms of electron volts, EV. So here, in the case of hydrogen atom, okay, so only one ionization potential is exists here, because it can have several excitation potentials. So if more than the one atom, that means more number of electrons which are going to be present here, so that here also, which there can be more than one ionization process. That means with the energy which is required to remove the outermost electron, definitely it is needed here ionization potential. And also for the energy required to remove the second electron also. Why? Because of more than one electrons are there per second electron, and which is also more attached to the nucleus. So that is called second ionization potential. And like that here ionization potential which is going to be gradually increases. So for example, here you can see here helium atom. So which has two ionization potential. One is the 24.5 electron volts, and another one is the 78.6 electron volts. So these critical potential which can be determined experimentally by the Frank and Hertz experiment. So that you need to know that this is the apparatus. Here it is the glass tube which is going to be filled by a gas here. So you need to calculate that critical potential, which is determined at the pressure of 1 millimeter of 1 mm of mercury. So here this is a variable potentiometer battery, and another battery is B3, so milliampere. So that you need to calculate that. And this is the filament here. Bulb is here. B is the bulb. So a bulb consists of filament. So here anode to here, what do you say here? Plate. So that how the electrons which are going to be moving here. So that we need to read it carefully, so you can easily understand that. So what are the accelerating potential by the collector current here? From the graph you can easily calculate. But in this first block here, uh, what are the questions, model questions which is going to be gives to you. So these are the questions here. One is that uh, see here Bohr's theory, and also vector atomic model, and finally in that Frank-Edge experiment. So these are the short questions. What is line spectra? Briefly, you can explain about the vector atomic model and discuss about why do you consider why what is the use of the Frank-Edge experiment here, how it is going to be calculated. Like next, we'll jump into the second one, quantum numbers. So in this quantum number, you need to discuss about the what is the correspondence principle, what are the quantum numbers, what is Pauli's exclusive principle, and periodic table of elements, and also molecular spectra. So this includes the what is the electronic spectra, rotational spectra, vibrational spectra. Okay, quickly you can go through. So here we have to study about the Bohr's correspondence principle and also Pauli's exclusion principle. So spectra means the emission of electrons, or you have to say that emitted by atoms due to the energy change in the electronic system. You can call it as a atomic spectra. Okay. In the molecular state, the spectra emitted by the molecules, that is molecular spectra. Atom is emitting atomic spectra. If electron is emitting electronic spectra. Okay. So like that here, more spectra in three distinct regions. One is that micro or far infrared region. So infrared region consists of two. One is that here near and far. So this is in far infrared IR region, and near next one is the near IR region, and also visible, which is near to the ultraviolet region, UV region. So we know pretty well about that the spinning of electron, which was proposed by the Gauss-Mead and Uhlenbeck. So which is this is the greatest advantage to explain about the double line structure of the alkali metals here. And also according to the Bohr, each atom of the element, that means atomic number Z, and also which can build from an atom of the electron atomic number, so that by Z minus 1 by adding one or more electrons to the lattice latter atom for the keep of the atom so form neutral. So it is necessary to increase the here nuclear change correspondence. What is the correspondence principle here? So this may be asked as a short question, but it is not important. What you need to know that according to the Bohr's theory, hydrogen atom, which is combining of the classical as well as the quantum theories. So the quantum number, which is n, which is very large, so that the allowed energy values, which are almost continuous. But when the case of the spectral lines, which is that means which is limited here, that means which are crowded to the n equals to infinity lines are there up to the n equals to infinity. So the spectrum, which is almost continuous, not in a discrete manner, there should not be a, which is going to be showing the splitting of the spectral lines, which are closer and closer to the each other here. So that you can call it as a almost continuous. So here, which is led to the Bohr's postulate of the correspondence principle, and also which is going to be stating that the prediction of the quantum theory for the behavior of an atomic system, which may be correspond to the prediction of the classical theory. So quantum theory, which is taken to the classical limit, so that the quantum theory is a situation of transition between the nearby states, which is having very large principal quantum numbers, and also which is going to be showing the quantum and classical theories to give the identical predictions for the radiated frequency V equals to h nu. Okay, so that the frequency, radiated frequency, is mu here. So Bohr has been used the principle to deduce the selection rules for the applied of the transition between the particular state in the atom sphere. So from which state to the which state, the electron which is going to be here jumping. That means the transition is going to be takes place from which level to which level. But according to the classical electromagnetic theory, which is also going to be predicts the frequency of the emitted radiation, which is equal to the frequency of the revolution, and also limit of transition between the nearby states. So which can have very large principal quantum number n equals to infinity, that classical theory, and also Bohr yields the same results. So this theory which is going to satisfy the correspondence principle. So here you need to know that what are the quantum number. Here for a hydrogen spectra, you can see that Bohr is going to be says that the electron which can be revolves around the nucleus in circular orbit, and later on Sommerfeld enter is to be says that not in a circular, the electron revolve in a elliptical orbit. So that here these orbits which are going to be playing a very important role here. So by the development of the atomic structure, so that here what are the statements which was given by the Sommerfeld here. He is going to be showing that the electron in any one of the allowed energy levels, any one of the allowed energy levels of a hydrogen atom, which may move from any one of the number of the atoms. So that the energy levels, principal quantum number n equals to 1, 2, 3. So these are the possible, and also n equals to 4 up to infinity. So these are the possible orbits. So what is the here you can see that the energy levels diagram here, the energy electron orbital for the hydrogen atoms. So you can see in which state the electron is in ground state. So this is the case here. GS means ground state here. Okay. See here. Ground state n equals to 1. But whereas n equals to 2 here, n equals to 2. For n equals to 2, there is a two possible numbers. That is here orbital angular momentum L equals to 0 as well as the L equals to 1. For n equals to 2, see here, for L equals to 0, 2s orbital, and also L equals to 1, 2p orbital. Same electron, only dot which is remain showing that the electron in which orbit the electron which is going to be revolved. So these are the suborbitals. See here. Similarly, see for n equals to 3, three possible values 0, 1, 2. Okay. So 0, 1, 2 means n equals to 3 means in 3s, and n equals to 3, 3p, L1, and n equals to 3 and L equals to 2, 3d. 3s, 3p, 3d. So these are the different orbits. Is it clear? Next. Yeah, you can see here n equals to 3. What are the L values? 0, 1, 2. So what is the diameter of the circular orbit which was given by the Bohr? So there must be a major axis of two elliptical orbits. See here, two elliptical orbits for L0, L1. So that the minor axis, which values may be 2 by 3 and 1 by 3 of the major axis. So see here L0, S, L1, P, 2, D, F, L4 is G, H, I, like that. So according to this, you can easily calculate the orbital angular momentum, that is PL equals to L into H by 2 pi. So that L values must be L into square root of L into L plus 1, and H by 2 pi must be H cross. Okay, most important objective bits while you are going to be writing the competitive exams like group 1, 2, 3, 4, like that. Next, you can see here. This is 6564 angstroms, which is related to H alpha. Okay. So for yellow color, you can see here how the splitting of the spectral lines for a sodium. This is for sodium color, and this figure, which is for hydrogen, Balmer series. That means H alpha, Balmer, Lyman, Balmer, Passion, Brackett, Fund. Different series are there. Na? Here there should be a closely packed of how many angstroms here? 1.59 angstroms. But here for yellow color, 5890 and 5896. So that in our laboratory, while you are doing a diffraction grating or resolving power of a grating, okay, and also so many resolving power of a telescope, there you have to use a yellow color light. Yellow color light means here sodium vapor lamp. So that what is the how the splitting of the spectral lines you can easily see there experimentally in our laboratory. మీరు కనుక మీరు ప్రాక్టికల్ చేసినట్లయితే మీకు అక్కడ ల్యాబ్ లో చూపిస్తారు మేడం. సో మనకేంటి రిజాల్వింగ్ పవర్ ఆఫ్ ఏ గ్రేటింగ్ ఎక్స్పెరిమెంట్ ఉంటుంది. అందులో మీరు ఈ లైన్ స్పెక్ట్రా గురించి మీరు చూడొచ్చు డైరెక్ట్ గా. మీరు యూనివర్సిటీకి వెళ్ళినప్పుడు ల్యాబ్ మీరు చేస్తూ ఉంటే ఫిజిక్స్ ల్యాబ్ లో, ఆప్టిక్స్ ల్యాబ్, యూ కెన్ ఈజీలీ సీ దేర్, అబ్జర్వ్ లైవ్లీ హౌ ద yellow light which is going to be showing the two spectral lines. So అందులో ఒక దాని యొక్క వేవ్ లెంత్ ఏమో 5890 and another one is the 5896 angstroms. 1 angstrom is 10⁻⁸ centimeters. మనం యావరేజ్ గా ఎట్లా yellow కలర్ ఎంత తీసుకుంటున్నాం అండి? 5893. Okay. So what is the difference of these two D1 and D2 lines? D1 and D2 lines అంటాం మనం ఇది సోడియం కలర్ కి. 6 angstroms is there. Okay, like that based on this you can easily here shows the structure of the spectral lines for different whatever the atomic number is to be considered here. So you need to draw. So that what are the 4 quantum numbers? Principal quantum number, orbital, total angular momentum, angular quantum number, and magnetic. Okay, so that these are the n, l, j values must be l plus or minus s, and m r, n, and l, ml, ms. So that you need to specify in the examination portions. Next, most important short question, Pauli's exclusion principle. So here what are the here states of the electron which can be specified by the 4 quantum numbers here? Principal quantum number, n values, so that which can determines the size of the electron orbit and also arises the quantization of the energy. Next is the orbital quantum number, which is to be denoting here small l. The values must be 0 to l minus 1. Okay, so and this determines the shape of the electron orbit and also arises from the quantization of magnitude of the orbital angular. Next, the ml values, magnetic quantum number. These values are minus l to plus l, which can determine the orientation of the orbit in space, arises from the quantization of the direction of the orbital angular. Next, the ms value, spin quantum number. These values plus or minus off, which can determines the spin orientation, whether it is an upward direction or downward direction, which is also arises from the quantization of direction of the spin angular moment. So here how the quantum number for the electrons in an atom. So the Pauli, he has been introduced a principle which is known as exclusion principle. According to that, no two electrons can exist in an atom in the same electron state. Okay, no two electrons, so that it can exist in an atom in the same electron state. So that different quantum numbers are there. You know that N, L, M, L, S, M, S. So that here electron which is having the same n values, which consist of the cell group or level, and also which is having the same n but different values. That means L values which to be constituted for the suborbitals. That means subshells and also subgroups or sublevels. So that n consists of the subshells and corresponding possible values for the L values. So for the spectral notation, with the electron which is having the orbital angular momentum or quantum momentum 0, 1, 2, 3. So these are to be called it as a SP. L equals to 0, S suborbital, and L equals to 1, P, L equals to 2, D, F, like that. But in the X-ray spectral notation, the shells with N equals to 1, 2, 3, 4. So that is to be denoting here K orbital, L, M, N shells. Shell or orbital, whatever it may be. You need not to worry here. But L values orbital angular momentum 0, 1, 2, which can gives the subshells SPDM. But whereas the N values, principal quantum number N 1, 2, 3, like that, which is designated by the KLMN shells or orbits. So the maximum number of electrons which can be occupied by the cell, which is the formula is 2n square. Okay, so you need to remember that equation. And also here one formula is given out here. The L values, how to calculate the values, 2 into 2L plus 1. By substituting this equation, you can have the values. The distribution of the electron in different shells and subshells. See here, see here. This is N equals to 1, okay, and L0, N1 means L0, ML0, MS values is plus of and minus of. So what is the maximum number of electrons which can be occupied with the first cell? N equals to 1 means formula is 2n square. So the 2 into 1 square. 2 into 1 means 2. Therefore, the total number of electrons which can be occupied in the shell is 2. So that's why here in electronic configuration 1s2 subshell maximum is 2 electrons. Similarly, I just want to write it down. See here. Formula is 2n square. 2n square. Okay. If n is 1, how many? 2 into 1. That means 2. Which one? The maximum number of electrons. Okay. Next, if n equals to 2, n2 means L values 0 and 1. L values is 0, 1. What is ML values? 0, minus 1, plus 1. But spin values are same. MS values, plus of to minus of. But here you can calculate. N equals to 2 means 2. How many? 2 twos are 4, 4 twos are 8 electrons. See here. Okay. How, sir? See here how many? 2 electrons. Here how many? 6 electrons. Total is 8 electrons. Similarly, n equals to 3, 18. 18 means 6 plus 2 plus 10. Total 3 orbital. Third subshell. How many? 2 plus 6 plus 10? 18. Like that you have to calculate. ఓకేనండి, మీకు ఏమైనా డౌట్ ఉంటే అడగండి. సో లైక్ దట్, యా ఇక్కడ ఇచ్చినట్టు చూడండి, ఫార్ములా ఇచ్చినట్టు 2n square ఫార్ములా. సో బేస్డ్ ఆన్ దట్, a shell of principal quantum number n is having 2n square electrons is said to be completed. And also a subshell of orbital quantum number Small l is said to be completed. Orbital lo manaki etla andi formula 2 into 2l plus 1. Okay, 2 into 2l plus 1. See here. Yes. So which is about the Pauli's exclusion principle. Next, periodic table. You need not to be worried about that periodic table here. The electronic configuration of ionization energies which are given out. Hydrogen. See here, 13.6 electron volt. Most important bit. Okay. What do you say? Z. Z is the atomic number. So that in K shell, L shell, M, N, like that here. How the electrons. So that for hydrogen, how to write the electron configuration? 1s1. Helium is 1s2. So here 1s2, 2s1, like that. Here 2 electrons are there. In K shell, in L shell, 1 electron is there, like that. Yeah. You just know about that. What is a molecular spectra? Electronic, rotational, and vibrational. So molecular spectra arises due to the transition between the allowed energy states of the molecules. So here the energy level which is completed then of the atom here. This is due to electronic angular momentum is not conserved in molecules. The molecular energy state cannot be specified in terms. So for a diatomic molecule, di means two molecules are there. If you say that O2, N2, okay, F2, all these are diatomic molecules. So that the total charge distribution which is symmetrical about the internuclear axis, and also the angular momentum is also going to be conserved. So here the nuclear motion in molecules cannot be neglected. For a diatomic molecule, nuclear vibrate about the internuclear axis. So internuclear axis means two molecules are there. So there only you have to be consider that O2. So that O molecule, internuclear axis, like that. And it may not be asked, but you need to know the definition of this. We will give the counseling. So summary here, what is principal quantum number, how it is determines, and also orbital, spin, ML, MS. ఇందులోంచి పక్కా 100 కి 70% ఉంటుంది. You need to know that 70% question is going to be coming out from this. Okay. Next, what are the questions? See here, state and explain Pauli's exclusion principle. You need to be focused on that, and also Bohr's correspondence principle. Next, block 2, elements of quantum quantitative theory. What are the elements? Photoelectric effect. Okay. Wait a minute. So you need to know about that. What is photoelectric effect? Wait for 1 minute. I just want to show you the PPT here. photoelectric effect. So who proposed this photoelectric effect? The greatest revolutionary has been taken out. So fiber optics too. Yeah. I think so. You can able to see this. See here. What is the photoelectric effect here? The emission of electrons from a metal plate. So that metal may be alkali metal here. When the light which is going to be incidenting upon this, or else other radiation which is having such a wavelength or a frequency, which is going to be incidenting upon this, the electron which is going to be emit from that metal plate, that you can call it as a photoelectric effect. So simply, the emitted electrons, you can call it as a photoelectrons. The entire phenomena, you can call it as a photoelectric effect. So who discovered this? Hertz. He has been allowed a ultraviolet light to fall on a zinc plate here. So this is a alkali metal. So that he has been verified, experimentally verified by Alvachs, Leonard, J.J. Thomson, R.A. Millikan, and others. So that this photoelectric effect, so many metals they have been experimentally discovered how the photoelectrons rate which is going to be giving out by the different types of metals, they have been performed so many experiments. Next, Millikan, he has been investigated affect a large number of alkali metals, so many. So with a wide range of frequencies, light frequency, so that frequency is also going to be changes, light frequency. And later on, we got a Nobel Prize in 1922. Who? Millikan. Next, experimental study of photoelectric effect. Quickly, I can. So this is the experimental study. You can see here. So this is a evacuated glass tube. You can see this is a quartz window, and S is a source here. Source means light. So that this quartz tube, which may consist of a photosensitive plates, cathode, C means cathode, A means anode, and series you have to be connected a commutator, and potential difference, rheostat, battery, as well as the microammeter. To measure microammeter means to measure the current, volt. V means to apply the potential difference, rheostat changing the resistance, and battery. Okay. By applying, why do you need this circuit? A metal plate. So that see here, what do you say? See, so that this is a source here. The source which is going to be passing through the closed window and incidenting here. Light is going to be incidenting. The electrons which is going to be emitted, but it has to accelerate from the cathode to the anode here. How it is possible? By applying this voltage, by applying such a potential to this plate here, then only these electrons, photoelectrons, can move from the cathode to the anode by applying this. So that if you change the voltage, more number of electrons which may move from the cathode to the anode plate. That means which may constitute more current. That is to be measured here by choosing the ammeter here. Is it clear? So like that, we need to do the practice. Okay, in practical also there is an experiment, photoelectric effect. Okay, Nandi. మీరు చూస్తే మీకు అర్థమవుతుంది. So whatever I said here, so see here, this consists of two photosensitive surfaces, C and A. C is the cathode, A is the anode. So this is a evacuated quartz tube. The plate C, which is connected to the negative terminal of the potential divider. So this is the potential divider, that like a commutator, and the plate A, which is connected to a positive terminal, and cathode is connected to the negative, and anode is connected to the positive terminal. So simply through the galvanometer, which is not shown in this, so that by a micrometer or else a micrometer, microammeter. Next, so see the concept here. Whenever a monochromatic light which is going to be incidenting upon this, which one? Plate C, metal plate. C is a metal plate. So that according to the definition, the metal plate which is going to be emitting the electrons. So if it is going to be emitting the electron can move from the cathode plate to the anode plate when it is possible by applying such a potential to this. So the number of electrons emitted and their kinetic energy depends upon the following factors. One is the potential difference between the two electrodes. Another one is the intensity of the incident radiation, and also frequency. If we change the frequency, different types of what, sir, how do you change the frequency of the light? పౌనఃపున్యాన్ని ఎట్లా మారుస్తారు సార్ అంటే, సోర్స్ దగ్గర మనం అక్కడ ఫిల్టర్స్ ని పెట్టినాం అనుకోండి. ఇఫ్ యూ కీప్ ది డిఫరెంట్ టైప్స్ ఆఫ్ ఫిల్టర్ అంటే 7 కలర్స్ ఉన్నాయి కదండి, రెడ్ కలర్ కానీ, ఎల్లో కానీ, ఆరెంజ్ కానీ, గ్రీన్ కలర్ లైట్ కానీ. మీరు ఇదంతా ఎక్స్పెరిమెంట్ ఉంటుందండి మీకు ల్యాబ్ లో, ఈ గో దేర్ యూనివర్సిటీ, so that you can easily find out. And also here, what is the metal is to be using here? Okay, a type of metal use chestunnam, is that metal is going to be emitting the electrons? So that is also to be checked. Next, what are the characteristics? So here, see here, what is the stopping potential, what is the saturation current here? That means you need to know that here, when the plate C is which is keeping the intensity and frequency, so that is to be fixed here. The potential difference between the plates, that means C and A, which is going to be showing the photoelectric current. That means number of emitted electrons, which is a function of potential difference. More potential, see here, on x-axis V, on y-axis I. More potential, more current. But maximum potential is to be applied by reaching, so saturation means stable. By reaching the maximum current, it comes to the saturation current. But what is the stopping potential? At what potential the current should be zero? See here, the current should be zero. ఇక్కడ ఏమవుతుందండి, current should be zero, I should be zero. At what potential the current, okay, the current that should be zero, that is called stopping potential. మీకు సింపుల్ లాంగ్వేజ్ లోనే చెప్తున్నాను, యాక్చువల్ అయితే ఇది డిగ్రీ వర్క్, రెగ్యులర్ డిగ్రీ వర్క్ సంబంధించి. సో see here, so what is the saturation current? See, the photo current reaches the maximum value. Photo current maximum వచ్చింది, దాన్ని ఏమంటారు ఇక్కడ? Saturation current. Next, intensity of incident radiation. So see here, different intensities. Low intensity means you will get the low current. High intensity, high current, high saturation current, low saturation current. Is it clear? See, ఇదే మీరు ఎక్స్పెరిమెంట్ లో చేసేది, స్టాపింగ్ పొటెన్షియల్ వర్సెస్ ఫ్రీక్వెన్సీ. సో at what voltage the frequency should zero, that frequency you can call it as a threshold frequency. See here, yeah, at frequency nu naught the stopping potential is zero. then the frequency mu naught is called as threshold frequency. So the wavelengths correspond to the threshold frequency. You can call it as a threshold wavelength. So see here, different alkali metals. It has been checked, and what is the light frequency? Frequency is also going to be changes here according to the retard potentials. See this. What is Einstein's photoelectric equation? Okay, so this we will discuss in tomorrow's class. We are going to be concluding this. Tomorrow we will discuss about the here Einstein's photoelectric equation. సార్ మరి అది ఉన్నదా మనకి సిలబస్ లో అంటే ఎస్ 3.3 చూడండి. సో యూ నీడ్ టు హ్యావ్ photoelectric equation. ఈక్వేషన్ ఖచ్చితంగా ఉంది, ఎక్స్ప్లెనేషన్ ఉన్నది. Later on we will discuss about the Compton effect. Tomorrow we will discuss, we can conclude this entire block 2. Okay, if you have any queries you can ask me directly. Right, all the best.